For over a century, physicists have been intrigued by the idea of black holes, with the concept gaining traction around 1916. These cosmic anomalies are among the most captivating and enigmatic phenomena we know, sitting at the intersection of vast gravitational forces and a peculiar invisibility to our understanding. A black hole, potentially weighing as much as 2 to 4 million times the mass of our Sun, remains a mysterious presence in the cosmos. Despite decades of intense research, our understanding has expanded from almost no knowledge to piecing together more details, with even more discoveries being made recently. A breakthrough by Michio Kaku has revealed startling insights about the interior of black holes, which may challenge our long-held assumptions and offer new perspectives on the nature of these celestial bodies. This new information opens doors to deeper explorations into what might have been overlooked until now. Join us as we venture further into the fascinating world of black holes and uncover what's hidden within. The universe is vast and awe-inspiring, but what exactly are black holes? Before we delve into the latest findings by Kaku, it's essential to revisit the basic understanding of black holes. While most of us have at least a general sense of what a black hole is, there are still some key elements that remain unclear. In 1916, Albert Einstein's groundbreaking theory of general relativity predicted the existence of black holes. At that time, the notion was purely theoretical. It wasn't until about 50 years later that evidence confirmed black holes as real objects in space. This revelation came in the 1960s during studies of the star X-1, a luminous celestial body emitting X-rays. Observations showed that these X-rays were not just randomly moving but were being drawn into a dense, invisible mass. This mass, later identified as a black hole, changed our perception of the cosmos. The discovery was monumental, proving that black holes were not figments of Einstein's imagination but tangible, elusive entities warranting further investigation. Following this breakthrough, scientists worldwide began a quest to uncover more about black holes. Their efforts led to the realization that the Milky Way alone may host around 100 million black holes. However, due to the challenges in detecting them, this estimate remains imprecise. Even though black holes are incredibly difficult to pinpoint, scientists believe that millions of these massive entities are hidden within our galaxy, making it even more crucial to understand them. Breaking down the core concept. Gravity. Black holes exert such immense gravitational forces that anything entering their domain is squeezed into a singularity, a point where the laws of physics as we know them cease to function. In simpler terms, black holes are like gigantic vacuum cleaners, pulling everything into them. One of the most terrifying aspects of studying black holes is that if someone were to fall into one, they would gradually stretch out and become part of the singularity. Their body would be torn apart by the intense gravitational forces before reaching the point of total destruction. It's best to avoid getting too close to one. Though they are scattered across the universe, the nearest black hole is nearly 500 light-years away. Even so, their proximity still raises legitimate concerns. In 2021, scientists achieved a historic milestone by capturing the first clear image of a black hole, the M87 black hole. This achievement was the result of numerous nights spent taking photos and aligning them to create a single cohesive image. As more data was gathered, researchers discerned that black holes consist of 3 distinct layers, contrary to the common misconception that they are just endless voids. 1. The event horizon. This marks the point beyond which nothing can escape. Once something crosses this boundary, it is inevitably drawn toward the black hole. 2. The photon sphere. Here, light itself gets trapped, unable to escape due to the powerful gravitational forces at play. 3. The singularity. All matter is compressed into an infinitely small point, where the very fabric of reality collapses and all known laws of physics break down. The unique nature of black holes. What's even more intriguing is that each black hole is unique. While they follow the general 3-layer structure, their behavior can vary significantly, making them particularly challenging to study. Conventional scientific methods don't apply to black holes, forcing scientists to investigate these anomalies through indirect means, such as analyzing the radiation they emit or studying the gas and dust swirling around them. Sending a probe directly into a black hole would be futile, as anything that crosses the event horizon is inevitably pulled toward the singularity and crushed into nothingness. This unavoidable fate means billions of dollars cannot be spent on probes that would meet their end before offering valuable data. Consequently, researchers are left to study black holes in 2 dimensions despite their 3-dimensional singularities. Adding to the complexity of black hole research is the fact that no 2 black holes are identical. When studying them, we must account for the breakdown of physics as we know it. The origins of black holes. Theories suggest that black holes form when massive stars energy to counterbalance the inward pull of gravity, leading to its eventual collapse into a black hole. If the star is massive enough, this process continues until the collapsing matter becomes a singularity. To further understand black holes, NASA scientists turned their attention to the center of the universe, particularly the M87 galaxy. There, they observed a powerful whirlpool of hydrogen gas spinning at mind-boggling speeds of 1.2 million miles per hour. The centrifugal force should have caused this gas to fly apart, but instead, it remained intact, suggesting the presence of a massive object at the center, likely a black hole. This object is believed to weigh up to 3 billion times the mass of our Sun. Theories of rotating black holes and wormholes. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe the behavior of rotating black holes. He argued that rather than collapsing into a point, a rotating black hole forms a thin, ring-like structure known as the ergosphere. This rotating disk of matter is key to understanding the breakdown of physical laws in the vicinity of black holes. Kerr's model also predicted the existence of an Einstein-Rosen bridge, a theoretical wormhole that could provide a shortcut through spacetime, connecting distant regions of the universe, or even parallel universes. To grasp the idea of a wormhole, it's important to understand spacetime as described in Einstein's theory. Spacetime is a 4-dimensional fabric warped by objects with mass, creating gravitational fields that influence the movement of other objects. Imagine spacetime as a piece of paper. If you fold the paper, you create a shortcut between 2 points. This shortcut is the essence of a wormhole, a passage through spacetime that could connect distant locations almost instantaneously. One of the greatest challenges in modern physics is unifying general relativity, which describes gravity on a cosmic scale, with quantum mechanics, which governs the behavior of particles at the smallest scales. Black holes, particularly their singularities, represent the ultimate clash between these 2 realms. While general relativity predicts the formation of singularities, points of infinite density, quantum mechanics suggests that such infinities should not exist in nature. Scientists suspect that a quantum theory of gravity is necessary to fully comprehend what happens at a black hole's core. The most promising candidates for this theory include 1. String theory suggests that particles are not point-like objects but rather tiny vibrating strings. In this framework, black holes might not collapse into singularities but instead form exotic states of matter. 2. Loop quantum gravity, LQG, proposes that spacetime itself has a discrete, granular structure at the smallest scales, preventing the formation of true singularities. Instead of an infinitely dense point, a black hole's core could be a Planck star, an incredibly dense but finite object. 3. Holographic principle suggests that all the information inside a black hole might actually be encoded on its event horizon, hinting at deeper connections between gravity, quantum mechanics, and information theory. These ideas, though highly theoretical, could help resolve the long-standing paradoxes surrounding black holes. The black hole information paradox. One of the biggest mysteries in black hole physics is the information paradox, first proposed by Stephen Hawking in the 1970s. According to Hawking, black holes slowly evaporate over time due to Hawking radiation, a process where virtual particle pairs form near the event horizon, with one particle escaping and the other falling in. This leads to the gradual loss of a black hole's mass. The paradox arises because quantum mechanics dictates that information cannot be destroyed. However, if a black hole eventually evaporates completely, what happens to the information about everything that fell inside? Does it disappear forever, violating quantum principles? Several theories attempt to resolve this dilemma. Hawking's revised theory. In his later years, Hawking suggested that information might escape back into the universe through subtle quantum effects. Firewall hypothesis proposes that an extremely hot firewall exists at the event horizon, burning up any information before it enters the black hole. Holographic principle suggests that the information is not lost but encoded on the black hole's surface, meaning it never actually disappears. If scientists can solve this paradox, it could lead to a breakthrough in understanding both black holes and the fundamental nature of reality itself. Black holes and the fate of the universe. Beyond being cosmic anomalies, black holes may hold the key to understanding the ultimate fate of the universe. Theoretical models suggest that as the universe expands, black holes could play a crucial role in its long-term evolution. 1. The Big Freeze. If the universe continues expanding indefinitely, black holes will eventually evaporate through Hawking radiation, leaving behind a cold, dark void. 2. The Big Crunch. If gravity eventually overcomes expansion, the universe might collapse back into a singularity, possibly forming a new universe. 3. The Big Bounce. Some theories propose that black holes could serve as tunnels between different universes, meaning our own universe might have emerged from a black hole in a previous cosmos. Future observations and experiments. While many of these theories remain speculative, future experiments and technological advancements could provide definitive answers. Some key areas of research include: the Event Horizon Telescope, EHT, continues to capture images of black holes, improving our understanding of their structure and behavior. Gravitational wave detectors. Observatories like LIGO and Virgo are detecting ripples in spacetime caused by black hole mergers, providing direct evidence of their interactions. Quantum simulations. Scientists are using quantum computers to simulate black hole physics, offering new insights into their quantum properties. Next-generation space telescopes. Future missions, such as the James Webb Space Telescope successors, could probe the environments around black holes with unprecedented detail. Conclusion: the endless mystery of black holes. Despite decades of research, black holes remain one of the greatest enigmas in modern science. Every new discovery brings more questions, pushing the boundaries of our knowledge about space, time, and reality itself. Whether they hold the key to wormholes, parallel universes, or even the origins of the cosmos, black holes will continue to captivate and challenge scientists for generations to come. As research progresses, one thing remains certain: our journey into understanding black holes is far from over. The answers may lie just beyond the event horizon, waiting to be uncovered. One that brings together gravity with quantum mechanics, this hypothesis, frequently alluded to as the hypothesis of everything, is a journey that numerous physicists, including the famous researcher Michio Kaku, have sought after for quite a long time. One promising possibility for this hypothesis is superstring theory, which suggests that subatomic particles are actually tiny vibrating strings. The theory proposes that these strings create the fabric of the universe, explaining gravity as well as the phenomena surrounding black holes and wormholes. However, superstring theory also requires the presence of extra dimensions of spacetime that are so small they are impossible to detect with current technology. Despite the challenges, the quest for understanding black holes, wormholes, and the fabric of spacetime continues to captivate scientists, offering the potential for groundbreaking discoveries that could reshape our understanding of the universe. The quest for a unified theory. Continuing from where we left off, the search for superstring theory and other theories that aim to unify the fundamental forces of nature is an ongoing challenge. However, it holds the promise of unlocking new insights into the very nature of reality itself. These theories suggest that the universe consists of more than the familiar three dimensions of space and one of time. In fact, they propose that extra dimensions exist, but they are so tiny and compact that we cannot observe them directly with current technology. However, their existence could provide the key to understanding phenomena like black holes, wormholes, and the deepest mysteries of the universe. Superstring theory offers a fascinating picture of the universe, suggesting that all matter and forces are manifestations of tiny vibrating strings. These strings can vibrate at different frequencies, with each vibration corresponding to a different particle, just as a guitar string can produce different musical notes depending on how it vibrates. The fundamental particles of nature could correspond to various vibrational patterns of superstrings. If proven, this theory would not only provide a unified explanation for the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, but also open up entirely new ways of understanding the structure of the universe. This could potentially answer some of the biggest questions in physics, including the nature of dark matter and dark energy, which together account for the majority of the universe's mass and energy yet remain largely mysterious. Challenges in testing superstring theory. Despite its elegance and promise, superstring theory remains unproven. One of the major obstacles in testing the theory is that the extra dimensions it predicts are so microscopic that they are beyond our current observational capabilities. Detecting these dimensions would require instruments of unprecedented sensitivity and precision, and even then, the evidence might be indirect. This makes superstring theory a challenging subject to test using traditional scientific methods. However, its mathematical elegance and internal consistency make it one of the most compelling ideas in theoretical physics. At the same time, scientists are also exploring other approaches that could lead to breakthroughs in our understanding of black holes. For instance, quantum gravity is another field of research that seeks to merge the principles of quantum mechanics, which govern the behavior of subatomic particles, with general relativity, which explains the behavior of massive objects like planets, stars, and black holes. The hope is that by combining these two theories, scientists can gain a clearer understanding of how gravity operates at the quantum level, thereby gaining deeper insights into the nature of black holes and other cosmic phenomena. The intersection of quantum mechanics and general relativity. The intersection of quantum mechanics and general relativity is particularly crucial when studying black holes. This is because the extreme conditions near a black hole's event horizon, where gravity is extraordinarily intense, demand a theory that can account for both quantum effects and relativistic effects. In fact, the interior of a black hole, where the singularity exists, is one of the most perplexing and extreme environments in the universe. The singularity represents a point where space and time become so distorted that the usual laws of physics break down. Understanding what happens in such a place requires a theory that can reconcile quantum mechanics and general relativity. This has led to the development of ideas such as loop quantum gravity and other quantum gravity models, which aim to resolve these inconsistencies and provide a more complete picture of black holes. As we continue to probe the mysteries of black holes, one thing is certain: the more we learn, the more we realize how much there is still to discover. Black holes are not just points of destruction but also regions of incredible complexity and potential. Whether they serve as gateways to other dimensions, as some theorists believe, or whether they hold the key to understanding the deepest secrets of existence, black holes remain a crucial area of study. As our tools and theories advance, so too will our understanding of these enigmatic objects. Future challenges and technological advancements. Looking ahead, the next major challenge will be refining our methods for observing and studying black holes. One of the most exciting advancements in recent years has been the development of gravitational wave astronomy. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as the merging of black holes. By detecting and analyzing these waves, scientists can learn about the behavior of black holes and other celestial objects in ways that were previously impossible. The detection of gravitational waves has already provided groundbreaking insights into the dynamics of black hole mergers, and future experiments are likely to yield even more discoveries. In addition to gravitational waves, another promising area of research involves the use of advanced telescopes and imaging techniques. The Event Horizon Telescope, EHT, which captured the first-ever image of a black hole in the M87 galaxy, is an example of how innovative technology can shed new light on black holes. By combining data from multiple radio telescopes around the world, the EHT was able to capture an image of the black hole's shadow, offering a glimpse into one of the universe's most mysterious phenomena. As technology continues to improve, we will likely be able to observe black holes in even greater detail, revealing more about their structure, behavior, and role in the universe.